9:30, so let's get started. My name is Vishnu. I'm a first-year student here in the College of Arts and Sciences. I study music and math, as you might have guessed. Just a quick show of hands, is anyone interested in pursuing either of those or both in the future? College research, probably. Sure. They're very fascinating subjects, so hopefully to see. So, just a brief overview. First want to take you back to the beginnings of these disciplines. We'll look at very early history of both math and music and see how they're somewhat born out of the same ancestors, so to speak. And then we'll sort of look at how they progressed through history in a general trend. Then we'll look specifically at music in 4 different elements of music and how we find math in each one of those. There's plenty of listening examples for you to sort of hear, because if you just keep talking about it, it's sort of abstract. It's easier to listen to music. I have a handout here. I'm not passing it out now because I don't want to distract you. It doesn't really have anything useful. It's just a list of recordings so that if you find that you like what you hear today, you're welcome to listen to some more. Just my opinion of what good music is and where you'll find math in it. So I don't normally like quoting people, but this quote is just very apt. Has anyone ever heard of Leibniz, the mathematician? If you've ever taken a calculus course, you've probably seen a notation like this. I don't know what this means. Anyone take calculus? Oh, yeah, this is not a derivative. Well, this is a derivative, d of dx of some function. It just means the rate of change. Anyway, this notation is named after Leibniz, which is why I mentioned him. A German mathematician of the 18th century, and wasn't a musician, but obviously very knowledgeable about it. And he said, "Music is the pleasure the human soul experiences from counting without being aware that it is counting." So consider the implications of that. When you listen to music, perhaps you're not counting in the sense of 1, 2, 3 or whatever, but your brain is fundamentally a pattern-seeking device, is listening for groups of numbers or symmetry or other number-based patterns. So you're welcome to disagree with it, but I find it to be largely true, either on a conscious or a subconscious level. So let's look at the very beginning of math. What do you think that the first thing humans ever discovered or invented or created was in the field of math? Yeah, exactly, great, counting. Or specifically counting numbers. That was our first creation. Counting numbers, also known as natural numbers, start at 1, and you just count them, 1, 2, 3. No fractions, no decimals yet, because they don't have any immediate practical application. But the first thing we encounter in math is counting. We're talking tens of thousands of years ago, when probably what happened is some human, doing whatever they did back then, hunting, gathering, or whatever, and maybe find a basket of fruit and a basket of apples and a basket of oranges. And he says, there's something similar about this, but I don't know how to express it. Why don't we create the concept of quantity so that I can say that this number of apples is the same as this number of oranges, and thus we create numbers. You know what numbers are. One, you can, if I tell you, tell me what 1 is, you can hold up one finger, you can point to one thing, but actually it has no meaning outside itself, right? It's an abstraction, a symbolic expression of quantity. It's something that we've created sort of out of nothing. Math, all math, is based on these fundamental abstractions. We call them axioms. So, if you ever study a pure math course in college, you'll learn that there are several axioms upon which we base everything else. Calculus is based upon a set of axioms. Real analysis is based upon a set of axioms. An axiom is something that we take for granted. You can think of it as a property. You learn properties in pre-algebra, but you can't prove it because we just take it for granted. We use a very fundamental axiom called the reflexive axiom. We have some number x, doesn't matter what the number is, but we know that that number is equal to x. We can't prove this, it's just by convention, or by definition. It's called the reflexive axiom. Math is based off of a bunch of axioms just like this. So that's fine. So at this onset, when we create numbers, it's purely for practical purposes, right? It's so that I can count my sheep. It's so that I can count my oranges and my apples. I count how many animals I need to hunt for dinner or whatnot. It's a long time until math sort of gains independence from its subservience to practicality. That might be a mouthful, but consider that when we first started, it almost had a direct application to whatever we were doing. I need to count my oranges or apples. It's not until much later that we start studying math for the sake of math. The same thing in music, actually. So, some early evidence of math becoming independent, so to speak, is in Euclid's in Euclid's writing, Greek writer from about 300 BC. He writes about prime numbers. Prime numbers don't have any actual manifestation in nature, right? If you learn about prime numbers 2, 3, 5, 7, 9, sorry, not 9, 11, it's not going to help you count your sheep or your oranges, right? They have very abstract applications later on. You can use prime factorization to find least common multiples or whatnot. But at that moment, it doesn't have an immediate application. So that symbolizes that math has gone from something that was completely practical to something a little bit more abstract. The same thing sort of happens in music. What do we think, or what do you think, the very first instance of humans creating music was? What do you think the music was for? Or what do you think people was born out of? Any ideas? You can guess. Oh, I mean, someone raising their hand? Yeah, that's a great answer. And for a long time, that is true. So the true answer is we don't know, right? Written music in Western history sort of started around the 12th century, but music has always been around a lot longer. We have flutes and drums dating from tens of thousands of years ago. So we don't know what that music was like because there was no system of writing it. Probably it was for some practical purpose. Whether it's a drum to keep us marching in time, or some lullaby to send our children to sleep, something like that. It's not for a long time, and you're welcome to disagree with this. It's just a theory. It's not for a long time that music sort of reaches its own independence as well. So around this time, we have music as also a practical sort of thing. And you mentioned religion. That's a great point. So when Western music notation starts around the 12th century, it's all based on religious music, church modes and songs and things praising the god or king. One of the first examples we have of written music is called the Chansonnière du Roi, Songbook of the King. It's French. It's just a bunch of songs that people would sing in court. It dates from around the 12th, 13th century. So from that time up until middle of the Renaissance, maybe middle of the 16th century, 17th, that's when we start to have some music branching out from immediately subservient purposes. We have, the piano comes around in 1700, and even before then we have instruments, right? And then we have music that's written just for the sake of music. In the transitional period between music that was just for religion and then music for the sake of music, we have music for dances, for example. A very popular form of music in that time, in the 16th, 17th century, was dance music. Music for minuets, or gavottes, or sarabans, pavans, all these various classical forms of dance, and the music was written directly for that. It wasn't just meant to be performed alone, it was meant to accompany that. So as we can see in both math and music, we start with something that was something we create, an abstraction, and it has a direct purpose, the practicality. And then after a long time, we keep developing upon it and developing and developing, and it sort of takes its own independence. So we talked about Euclid and how he started talking about number theory and prime numbers, and we talked about the abstraction of music. I want to play you a little example. This is first a minuet from a Haydn symphony. A minuet is a type of dance. Franz Joseph Haydn was a composer in the 18th century, that we know as a classical period. So at this time, music has already reached its independence, so to speak. So this minuet is not necessarily meant to be danced to. It's part of a symphony. It's a concert piece, something we go to sit down and listen to. But it still has the characteristics of dance. The minuet is a triple dance. It's in 3, and basically goes like this. I don't know how to dance it. 1, 2, 3, 1, 2, 3, 1, 2, 3. And when you hear the music, you'll hear a very strong sense of 3, and you'll realize, Just take this 50 years ago and take it out of the symphony, and you could easily dance to it. It's a perfect minuet. Let's listen to just a few seconds. Might have turned off on me, so we'll wait for that to turn on. But I suppose you can imagine it in the meantime. Just the triple dance. The example I wanted to show you was that evolving from this. Was it on? Evolving from this, fast forward to 1,500 years, we have more symphonic music that's composed in the style of the minuet, but it's achieved complete independence. It no longer is danceable. So we have Beethoven writing the third movement of his symphony instead of the third movement of Haydn's symphony, and instead of a minuet, it's now called a scherzo. It's sort of an evolved form. And you'll realize it's still in triple meter. It sounds like a minuet, but it's impossible to dance to. You'll see why. Let's listen to the Haydn first. Hopefully it'll work out. Very danceable, right? Check out this is the third movement of Beethoven's Seventh Symphony. Not danceable at all. Still in three, still a sort of minuet form. I mean, when we were composing minuets as minuets, they had certain rules about them. It has to be in three, it has to have this period structure and whatnot. It still adheres to that, but it's achieved complete independence. No longer something you dance. You can try, but it's too fast. You won't be able to do it. So anyway, that shows you a specific example of how music went from something practical to something we created for the sake of itself. So before we continue, I want to tell you a little bit about music as an art. I mean, you must think the glaring difference between math and music is that one is sort of more sciencey, one is sort of more artsy, to use imprecise adjectives. But let me tell you a little bit about how some musicians or mathematicians in history have tried to quantify music and tried to build a formula around it so we can understand it better rather than just this big art thing that no one understands. So I'll give you three theories of aesthetic. Aesthetic meaning artistic value of music. The reason I'm giving you three is because it's this thing that no one agrees on. So I wouldn't just give you one and then have you believe it. I'll give you three different ones. You're welcome to believe whichever one you like or create your own. So one is, it comes from George Birkhoff, the mathematician, primarily mathematician, but also very interested in art. And his interest led him to write a book on quantifying beauty. Sounds like a very ambitious thing to do and probably sort of impossible, right? But I'll shorten the book version into the one fundamental equation he comes up with. M is a measure of aesthetic value. O is order, and C is complexity. Two or three very undefinable things in math, right? So order, in a very broad sense, is you can think of it as symmetry or recurrence of a theme. You know, say consider visual art. If we have something that's not very complex, say a stick figure. Not very complex, just a few vectors, long lines. We don't need a high level of order. It is symmetrical, but it's okay if I do this. It's still like a stick figure, even though that's not symmetrical anymore. It still has some artistic value. But consider a much larger scale piece of visual art, the ceiling of the Sistine Chapel, a huge fresco. There's no way that you can paint that entire thing and absolutely use no symmetry whatsoever. You lose the interest of the viewer. It's kind of hard to visualize, but imagine if you were to start from one end and paint the entire ceiling and then do completely new things for every square you come to. It just wouldn't be, you're welcome to disagree, but I just don't think it would be a very viewable sort of thing because you lose interest. There's too much things happening. So the more complex something gets, In order to keep the aesthetic value up, you would need to increase the order. So same thing in music. If we have a song, so to speak, something that's 3 minutes, you might have an introduction, a chorus, or a refrain, some sort of recurrent element. For a much larger scale piece of music, like a symphony, something that's 60 minutes, you're going to need a much higher level of order. And it has a very specific form. You introduce one theme, you introduce a second theme, then you invert these themes, you juxtapose them. You keep using the material that you've already introduced. You don't keep introducing new material over and over again. If you were to listen to a symphony of 90 minutes and you never heard the same thing repeated, you would lose interest very fast. And I don't mean repeated like exactly repeated, but say I give you one melody and then you never hear it again. Or you hear it after 90 minutes. You're not going to remember the melody, right? You're going to need to hear it again or hear some variation of it. As your complexity goes up, so must your order. So this is just one theory. This is George Vyakhov's theory of aesthetic. The second one I wanted to share with you is Leonard Bernstein, consummate American musician and conductor in the 20th century. He believes that music especially, he is well versed in the other arts, but music especially is defined or valued by ambiguity. Ambiguity means something being subject to multiple interpretations or something being unclear. And he says when we have a piece of music, our interest is kept because we don't know, we can't predict where it's going. It's a little bit hard to visualize, but we'll talk a little bit about the tonal system, the doctrine of tonality of music, how music was composed in that crucial second half of the second millennium. But the way it works is we have a home key. Say we're in C major, then C is the home key. Everything starts and ends in C. Leonard Bernstein's theory could be applied to a piece in C major, and we could say we start in C, then in the middle of the piece we're hovering around some other notes, and then before we come to the end, we're hovering around notes that are not related to C, like C sharp or F sharp. There's this ambiguity here, whether we'll be returning to C or not. We'll have a musical example of this later, so if it doesn't make too much sense now, it's okay. So that's his theory. Our interest is retained by this ambiguity. We don't know where it's going, so that's why we want to listen and figure it out. Third theory is from James Stewart. You probably know him because he wrote your calculus textbooks, or if you haven't taken calculus, you will learn about him because he's written the most widely used calculus textbook in the entire United States. He's also a musician, he's a violinist. His very basic and very approachable theory of musical merit is how many times you can listen to a piece without being singular. It's much more approachable for us, right? And I tend to agree as well. And it's almost striking how similar it is to this. When I listen to a very complex piece of music with lots of order, the first time I hear it, I don't hear all the order. It's just too much. Like a 90-minute symphony, I'm not going to remember every single melody. But the second time I hear more than I did the first time. The third time I keep hearing more. In theory, I could listen to it infinite times and I'd keep discovering new things. And it's kind of astounding how those two theories are kind of similar, but don't use any of the same notation. So that's 3 theories of aesthetics. Now you have an idea of how musical merit might be judged. So now I'd like to tell you about the doctrine of tonality. Tonality, you may not have ever heard of this word before, but it's sort of the system under which music was composed for a prevalent amount of time in Western music history. The reason I want to talk about this is because we can think of it as sort of the fundamental axioms of music. And yes, it doesn't apply to all music. It's sort of most prominent from 1700 to 1900. And you may think, well, it's just a fairly short amount of time, but the reason it's so prevalent is because, after 1900, when we evolved past tonality, it's still extremely pervasive in music of almost every genre today. So, 1700 to 1900 in the Western world, we were largely composing music that you probably know as classical music. And then after that, there's this huge creation of all these new genres. Tonality is prevalent in most of them, and we only see advanced versions of it recently. So I'll tell you a little bit about where tonality came from and why it's sort of logical and not just arbitrary. Same thing with math. This is the big fundamental connection I want you to get, that math and music are sort of born out of this logic. They don't come from nowhere. They're born out of formalized logic. So tonality goes all the way back before written music to Pythagoras. You must know Pythagoras from the Pythagorean theorem, right? The right triangle, and he says the length of this side squared plus the length of this side squared is equal to the length of this side squared. This is absolutely nothing with what I'm about to tell you. It's just Pythagoras theorem. So Pythagoras is one of our earliest music theorists. The story goes like this, although we don't know the exact details. He's walking and he goes to his blacksmith to do whatever you do at a blacksmith. And he sees the blacksmith's anvil, grabs a hammer and he strikes it, and he notices it makes a musical tone. Strikes it again and it makes the same tone. Picks up a different sized hammer, maybe it's heavier or longer or shorter or whatever, strikes the same anvil at the same angle and it creates a different tone. And it's predictable, he does it again and it creates the same different tone. And it's not just any different tone, it's very related to the first one. Anyway, what he discovered, or you could say invented, but it was more of a discovery because it's a natural phenomenon, is the harmonic series. What this means is that when we have a sound vibration, think of it as a wave, it's not just that fundamental tone that you hear. That vibration consists of a bunch of other vibrations that are sort of subdivisions of it. Hard to believe or visualize, but I'll try and explain it. So, consider one string held taut at two endpoints. We'll pluck it in the middle. Then the oscillation of that string will look something like this. Right? Here's the string. Here's the node of oscillation. And here are the two time states upon which it's oscillating. So, plug the string here, it's oscillating, and this is creating one frequency, or one tone, and it'll look like this, etc., etc. But it's actually doing everything less than this as well. Let me explain. So, as well as oscillating upon this node, every time the string crosses here, it's also oscillating upon these nodes. It looks like this. Same string, same node of oscillation here, and these are our second nodes of oscillation. The ratio of this to this is 2 to 1. So Pythagoras discovered that when you pluck a string like this, or hit a string, or hammer an anvil, it creates one fundamental tone created from this fundamental oscillation. Then the next overtone is what it's called, is also sounded. It's just not as clear. You may not be able to hear it because they're all sounding at once. It's sort of this vertical column of sound. But in modern instruments, the same sort of thing happens. Consider the way woodwind instruments work. You blow air through a column and then it's vibrated and amplified through the tubes of the instrument. A fundamental pitch is sounding, and a bunch of pitches above it are also sounding. You may think, oh, this is not true. You play one note and you hear one note. Yeah, you do hear one note, but the phenomenon of that note, as opposed to a pure musical, sine wave we can generate with a computer, is that one note created by the air column is actually vibrating at several other frequencies as well. And it has this quality called harmonics. And it's sort of difficult to hear because they're vertical. It's happening at the same time, but if you ever go to if you ever go see a very good symphony orchestra, they're very in tune with their harmonics. If they play one chord, or if they even play one note, if you listen closely, you'll be able to hear multiple notes. I would play you a demonstration, but it doesn't really come across in recordings. You need to hear it live. But if you listen closely to an instrumentalist playing one note, the next note you'll hear in that note, in that vertical column of sound, is the octave above it. What's an octave? It's just the same note, just sounded an octave. Using the word for its definition here, I'll play you an example. So here's a C. Here's an octave above it. So it's the same note, so to speak. It's just exactly twice the frequency. What Pythagoras discovered is that not only is this harmonic series prevalent, it's that for any vibration, we can consider the fundamental tone and all these frequencies above it. So say we have this fundamental, Then Pythagoras said the next one we hear is just 2 to 1 like this. The next one we hear is like this. Next one we hear is like this. They're all there. And as we get higher and higher, it's harder to hear them because they're just higher frequencies, and it's a big vertical column of sound, and you won't hear them all. I know it sounds like absolute rubbish, right? I mean, you hear one sound and you go multiple, that doesn't make sense. But it's true, and this is how tonality developed. So the basic premise was that the basic premise of tonality, the doctrine of tonality, the way musical thought was formed, is a hierarchy. It's a hierarchy that says one note is more important than every other note in a piece of music. It's not a democratic system. Right? Every note is not equal. In a piece of music, one note is the most important. Then the next one that's the next most important is this one right here. Because this one is the same note, just an octave above. This 3/2 relationship, if we multiply a frequency by 3/2, we get another note that's exactly between the 2 octaves. It's called the perfect fifth. So that's the next most important note. So let's just look at the letters we use for music notation today. We just use the letters from A to G. Tonality says that if we choose the key of C, it's the most important note. We're going to hear it the most. We're going to start and end our phrases with it. The next most important note is G. This is the fifth. This relationship right here is 3/2 the frequency of the C, and so on and so forth. This C to F right here is 4 to 5. And every other interval, music is created by intervals rather than actual frequencies. It is created by a simple integer ratio. I know it's a lot to take in, it doesn't necessarily make sense, but that's basically the way it developed. And you must be thinking, why do we have a system where the octave is divided into, it is divided into 12 tones. Between a C and a C, we count all the chromatics in between. We have 12 distinct tones. Why is it 12? Why is it not 20 or 50 or 100? Well, I'll try to explain it, hopefully I don't lose you, but what basically happens is we want the divisions between each note in an octave to be the same, right? Only then does it make sense to have something like a piano. Otherwise, if we have, divisions, if we have the same musical interval happening at different times, being a different span of frequency, that doesn't make any sense, right? We want it to be the same. So we want to subdivide the octave into a set number of intervals. So let's use our strongest distinct frequency. It's 3/2 right here. Our strongest harmonic is actually 2 to 1, but that would just create the same octave over and over again. So let's use 3/2. We want to multiply our fundamental by 3/2 over and over again until we eventually end back up where we were and we've subdivided the octave successfully. So we want 3/2 times some exponent, we call it A. And we want this to equal some octave repeated a number of times. This may not make intuitive sense, but if we go up from C in fifths, using the music notation, it would look like this. C goes to G, right? And then up a fifth from G is D. Fifth from D is A. Keep going. Eventually, after 12 times, you'll get back to C. And sure, even after 19 times, you'll also get back to C, or very close to it. You'll get to a C sharp. So why did we choose 12 and not 19? Well, consider this equation here. 3/2 of some exponent we want to equal 2 to some exponent. This is actually mathematically impossible. Let me show you what. So 3/2 to the A is the same thing as 3 to the A over 2 to the A equals 2 to the B. Multiply this over, we have 3 to the A equals 2 to the B times 2 to the A. This cannot be, right? You can't have these two even numbers to some exponent times this odd number to some exponent. It just won't happen. So we come up with an approximation. The approximation is roughly 7/12. What this tells us is that we should choose the fifth to be 7 subdivisions of the octave up from the fundamental, and you should choose for an entire interval 12 subdivisions. I know it's abstract, probably doesn't make a lot of sense. The point is really that this system that we came up with for developing music is not just arbitrary, not just someone decided we'll do it just because of that. It's rooted in physics. It's a natural phenomenon of harmonic series occurring when we have a fundamental tone. So it's sort of born out of logic in that sense. So that's a lot of abstract talk. As I said in the beginning, we'll listen to some music now, and we'll also talk about specific elements in music so that you can hear in a less abstract sense how it's connected to math. So let's consider 4 fundamental elements of music. Rhythm, melody, harmony, and form. Let's start with rhythm. Who can tell me what rhythm is? It's a little hard to define, but you could think of it as just the backbone of a piece of music as created by groups of numbers, right? Sort of the arithmetic side of it. So rhythm is obviously very important, and basic rhythms we find in music composed at the beginning of tonality in 1700. I mean, just the easy numbers, right? 1, 2, 3, 4. Each bar consists of those numbers of beats. So 2 things we find specifically in rhythm that we can think of in math are symmetry, of course, and this will come up later too, and also periodicity. You may not have heard this word before, but it essentially means that a phenomenon in math repeats itself. So periodicity applies especially well to sine functions or any sort of trigonometric function. Sine function looks like this. That's one period of a sine function, and then after that it just repeats. That's the second period, and it just goes on and on forever. This is periodicity of math. And periodicity also exists in music because we have a rhythm, and then that rhythm repeats itself. And in music, that's called an ostinato, when we have a rhythm that just goes on and repeats itself in a periodic fashion. Symmetry, I shouldn't need to explain. You understand what symmetry is in a visual sense. In a musical sense, it's just the same thing. We have, say, a rhythm of 3, and then something else happens, then we have the rhythm of 3 again. It's symmetry. We fold it along the middle and repeat the same. So let's listen to a little bit. It's hard to explain this or really tell you what it's about, but I want to play you a piece of music where you'll hear various groups of rhythms, and you'll sort of hear how periodicity and symmetry are exploited. It's difficult to explain it in concrete terms because you would need like a music theory background to hear it specifically. But listen for various rhythmic groups. You'll hear little fragments of rhythms. Maybe a group of 3, maybe a group of 2, and you'll hear it recurring. This is the 3rd movement of Anton Bruckner's 7th Symphony. Just listen to the first minute or so. It's just an opening statement. You'll hear several various rhythms introduced, repeated, and sort of manipulated. Oh, I think it turns off on me after it's wait a bit then. And I'll go to the next thing I wanted to say about rhythm is polyrhythm. After tonality has been used for 200 years, the basic trend in music history is that we've defined tonality in 1700. We have this very strong hierarchy of notes and very strong rules. We have to end on the same note we started with, or we can't have any dissonance for longer than a few beats. What happens over those 200 years is those rules are stretched and stretched and stretched until in 1900 they sort of break, and there's this big crisis of melody. So what happens then is composers start focusing on different elements of music to keep it fresh. They've said, we've sort of exhausted tonality. We can no longer use the system that we've been using for so long because we've used it already, and it would just sound redundant. So we're going to do interesting things with the other elements of music. This is some of the This is the time in the 1900s when polyrhythms become very prominent. Polyrhythm is just two different rhythms played at once. The most simple one is just 3 versus 2. So we have 1 unit of musical time, and we have in 1 unit 3 notes, and in another unit 2 notes. And over the same interval of time here, both of those rhythms are sounded. So consider a tempo like this. Subdividing that into 2 would just be, right? And subdividing that same tempo into 3 would be, right? And playing that together, see if I can do this, sounds a bit like. So my left hand is playing 2 and my right hand is playing 3. A little disoriented. But that's your most basic polyrhythm. And this grows and grows and grows, and soon in music we have 7 different polyrhythms stacked across one scene, and it creates this rhythmic dissonance, so to speak. You can't really tell where you are. In all music before this, you can easily tell what the time signature is, how many beats to a bar. You know, it's all based on dance forms, right? So we know exactly what it's like. So the second musical example I wanted to play for you is an example of a very, very heavy polyrhythm. You probably won't be able to tell what the actual beat is because there's so many polyrhythms sounding at once. But first, let's play that Bruckner excerpt, and you'll hear various rhythmic groups introduced and sort of ordered. Let's listen to that. Rhythmic group in that excerpt, perhaps you can't visualize it because you don't have the musical language, is this. It's a dotted rhythm, the dotted group of 3. It goes like this. One note is the quarter note plus a half a quarter note. That's what the dot means. One note is half of the quarter note just by itself. And then the third note is just a quarter note. Sound like this. That's one rhythmic idea we hear in there. Another one is just 2 notes. Much simpler, happens all the time. Another one is 3 notes. All 3 are sort of juxtaposed, but not vertically, so that you can hear them differently. So if you didn't understand any of that, it's fine. I mean, a lot of these things are sort of hard to hear, and take several listenings to get a hold of them. But that is what is happening with various rhythms. Now let's listen to an excerpt of polyrhythm, and if you can hear a single rhythm in this and describe it, I'll be very impressed, because I can't. Let's just hear a few seconds from Stravinsky's Rite of Spring. So actually what's happening there is we're shifting times every bar. Starts in 7/4, so we have 7 beats to a bar, then it goes to 5/8, so we have 5/8 notes in a bar, then 3/8, then 7/8, keeps sort of shifting. But there is a period to it. It's a very macro structure, and you'll realize it if you listen to the entire ballet, which is a few hours. But it is on some scale structure. Just and that microscopic fragment all we hear is rhythmic dissonance. So, I mean, those are 2 things in math we can sort of apply to rhythm. The other thing So let's go on. Let's talk about melody. This one's a little bit more interesting because it's very heavily tied to a branch of math that we probably know fairly well, geometry. Melody, the most characteristic thing about melody is shape. And shape is exactly a principle from geometry. So you can think of a melody as just a line having some shape. You don't need to think about it in terms of music notes or anything. You can think, say we start at the tonic here, and we go up, and sort of hover around here, keep going up, keep going down, we end back to the tonic. It's a very rough shape. There's plenty of ways you can have melody. You can have a melody that goes straight up, then down, then back up. Then, you can think of any number of geometric figures. And I want to tell you a little bit about transformations. You must have heard of transformations in math. Think of the xy plane, Cartesian plane like this. We have some figure, say like this. We can think of this as a melody. Something starts here, goes up, and stays there. This melody can be transformed geometrically in several different ways. Let's say we're in math and we want to translate it over the x-axis. Then what does it look like? It looks like this, right? And we can have this in music too. Starts at a note, goes down by the same interval, inverted. This one went up by it, and stays at a note below it. Yeah.
You said translate should be reflected.
Sorry, reflected over the x-axis. Let's reflect it over the y-axis. And it looks like this, right? In music, this would be, we start at the note above the fundamental note, and then come down and end there. Or say we want to reflect over the x and the y-axis, and it would look like this. These things that have names in math, like reflection and translation, also have names in music. This is called inversion. We take a melody and we invert it. This is called retrograde. We take a melody and we play it from forward to back. From back to forward instead of forward to back. This is called retrograde inversion. We not only invert the melody, but also play it from back to forward. There's also translation, which is very simple. In math, it just means moving a function uniformly to some other place. We can translate this over here. So say we do this instead. In music, well, horizontal translation doesn't make much sense. But say we do this. That's just the same melody, but played a couple notes lower. No big deal there. Or say, in geometry, you might have heard of dilation. That means the same figure sort of magnified uniformly, so it would look like this. This sort of thing exists in music. It's called augmentation. Basically, each time interval is being augmented. Instead of playing the C for 2 beats, we play for 4 beats now. Or the opposite of dilation. This looks like this. In music is called diminution. Instead of playing the C for 2 beats, we play it for 1 beat. 1 beat, 1 beat. So it's very simple. So all these geometric manipulations occur naturally, well, not naturally, we compose them in music to retain order. That's all part of order. We have these, if we were to just have one melody and then keep repeating it, we'd get bored of it very quickly. That's why we have all these geometric transformations that we apply to retain order, but not for us, so to speak. I want to play a very short excerpt of melody, and the reason I chose this is because it has a very distinct shape. You should be able to figure out the shape in just a few seconds. So the shape, I'm sure you can all think of it as well. So it goes like this, then settles, then back down like that. Very, very simple. That piece, Smithana's tone poem, Well Doubt, is created off of this melody. And there are other melodies too, but this very simple one, it just looks like a half circle, is used many, many different times with several different transformations. We won't listen to it all because it's a long piece, but that's it. That should give you an idea of how melodies have shape. So one master of this geometric transformation was Bach. You might know him, Johann Sebastian Bach. Many of the pieces he wrote use very few actual musical fragments or musical material, and everything is built off of this very sparse material that he's introduced at the beginning. let's listen to a piece. It's called a fugue. A fugue in music is where we have one melody or one theme. Say this is our theme. Bum, bum, bum. You know, you can think of that. And that theme starts in one instrument or one voice, and then it keeps going. And then at some point, some other instrument or some other voice introduces the same theme again. And then another one introduces it, but at a different, sorry, I keep misdrawing, but at a different time. And then soon we have all these voices or all these instruments playing the same thing at the same time, but in different registers or different pitches or different inversions. Yeah, so let's listen, and you'll hear the melodic fragment at the beginning. And you should be able to hear when the second theme enters, and it's the same as the first theme, it's just in a different register. Then you'll hear it again a third time. It's called a triple fugue. So that's the first theme. Obviously it's developed, but it's just the same theme repeated 3 times and juxtaposed in different registers and time to create that music. It's pretty interesting. Bach wrote a lot of fugues, and then they all have this wonderful symmetry and structure and logical flow. If you ever listen to them, the more times you hear them, the more things you hear. It's quite fascinating to track that one line is happening in the exact same manner over and over again in different places. Now let's go to harmony. This is probably the most erudite aspect, so I can't tell you a lot about it without going deep into music theory, and I don't want to lose you already after all that abstract explanation, so we won't spend too much time on it. But basically harmony is the vertical aspect of music. You can think of melody as the horizontal aspect and harmony as vertical. You know, melody has a shape, harmony doesn't have a shape, it just happens in vertical columns. Harmony means multiple notes sounded at once, and our system of tonality builds chords in thirds. Maybe that doesn't make sense, but in C major, we have the fundamental chord is C, E, G, because E is a third up from C and G is a third up from E. And the second most important chord is built on the G, right? Because G is 5 up from C. And built in thirds, this chord would be G, B, D. These 2 chords are very important in the key of C major because this one we call the 5 in Roman numeral notation. In music we use Roman numerals. This one is the 1. These 2 together create something called a cadence. At the end of a musical phrase, we will close it off with a cadence by going from 5 to 1. And this, the reason is this chord has a tendency to go here. You can think of tendency as sort of a pull. When we hear this chord and C has been established, when we hear a C major chord and whatever, something in C, then we hear this chord, it tends to 1. We want to hear 1 after that. That's why that cadence creates this sense of finality, of closing. Because this is our relationship of a fifth, which is the most fundamental integer ratio, which is 3 halves. This B is very close to the C, so it's leading there, it's just 1 step apart. And this B is very close to this E, just 1 step apart as well. And this G is common, it's shared. So these are the two this chord leads exactly with this one. You may not see the logic of it, but when you hear it, you'll realize, oh, we've come home. This is the end of the musical phrase. That's one thing that's important about harmony. And if we look deeper at harmony, I won't go into this because it's very erudite. There is also a very abstract sense of geometry. When we move from one key to another, a piece will not always stay in the same key. It will do something called modulation, where we change the tonal center. So we start at C, and then say we modulate to G. Now G is our new home. And if we want to drive home that G is our new home, we don't just play the G chord over and over again. What do? We create a cadence in G. So we use the fifth chord of G, which should be, what's the fifth up from G? G, D, and that chord is D, F, A. Why is this chord a 5 of this? Because same relationships, right? F goes to G, A goes to B. So if we're in C and we suddenly hear a lot of Ds, and then we hear a G, we know that we're no longer totally rooted in C, but that we've modulated to G. So it's sort of an abstract thing. So I don't have a musical example for you, but you can pick up one of these at the end and listen for yourself. Just because it's not very easy to hear unless you're initiated in it already. But once you hear it many times, you'll start to understand the geometry of harmony. It does exist. It's sort of abstract. The last thing that's probably the most important is form. What musicians call form, mathematicians call structure. It's almost the exact same thing. I want you to think of mathematical proof. We won't do one in the interest of time, but the way a proof works in math, you start out with a number of things that are given and a number of, and one thing that you want to show. So, say you're given, say we want to prove that the square root of 2 is irrational. We're given that 2 is a rational number. We won't do this proof because it takes a while. But we're given that 2 is rational. What does rational mean? Rational means that we can express it as an integer, as a ratio of two integers, say P and Q. And P and Q are just some whole numbers. We know that pi is irrational, right? Because we can't write pi as a fraction of two integers. It just doesn't work. And then we use this fact to show that this must be irrational. You know, we'll take a square root of that, and et cetera, et cetera. That's how the proof works. But essentially, the idea is we're given something, you know, we know something, and we want to show something from what we know. Almost the same sort of thing exists in music, at least in, you know, music of the tonal period. The composer gives you something at the beginning, and at the end, everything that comes, that results, that conclusion is logical from what we are already given. Especially in that Bach excerpt. You know, the way it resolved was by restating the theme in all three voices at once. At the beginning, he gives you the fundamental theme. That's what we're given to work with. Then it's repeated in another register. And it's repeated in yet another register. And then at the end, he ties it together by bringing that theme back in its original form. Same sort of thing happens in a symphony. And it's much harder to hear because it's such a long format. But, you know, in a 90-minute symphony, you're given X number of themes, and then those themes are developed upon in the four movements or however many, and then in the end, they're all tied back together. They're either played on top of one another, or if there's some resolution that was left unsolved, say there was some melody at the beginning that went like this, didn't go back home, then at the end you might hear something like this. And it's been like 80 minutes, so you don't remember it, but it has a sense of closing, a sense of finality. That's what the form is about. Both math and music share this structure that, you know, that has this logical flow. So we're running out of time, but I have one example for you here. It's a bit long, it's about 4 minutes, but the thing I want you to notice is that it has this quality of finality. What it does is it's the end of a symphony. So we haven't listened to the entire symphony, so we don't know what exactly it's closing. But you can imagine that it's tying up all the untied knots that we had throughout the symphony. What you'll hear is, so this is a symphony in E flat major. E flat is our home key. We want to end in E flat, right? So what you'll hear is a sequence of you can consider it harmonies. There's a figure in the strings that's going like this. This is E flat and this is F, the next note above it. So that's obviously creating some ambiguity, right? It's an oscillation of the strings. You're wondering, are we in E flat or are we oscillating around it? Are we ever going to, you know, is this sequence going to converge, or is it going to keep oscillating forever and ever, and we're never going to get home? Then above it, we have figures in the woodwinds and the brass, just playing some melodies, also an ascending sequence. Eventually we get to this final statement, the last few bars of the symphony, and the strings are still oscillating. It's not a musical sequence, but think of it as a math sequence. We're going from the dominant of E flat, 5 above it, back to E flat. We're sort of oscillating between the two most fundamental notes. We don't know whether we resolved or not. part of the beauty of this piece of music is that when it ends, we're still left with this sense of, are we actually done? Was that a close? It does end on an E flat, but since it's so abrupt, it's hard to tell whether it actually closed or not. It's about 4 minutes. Perhaps you won't be able to navigate through all of it, but at least listen for this in the last minute or minute and a half, and you should hear the ostinato or the oscillation from the strings, and so hear why it creates that ambiguity. It's the end of the 4th Symphony of Brooklyn. So this is 2 melodies happening at once. Same note. Goes to an octave. And then both of them go up and down respectively. This unit is repeated thrice. You can hear this already. It's very soft. Now we've gone into another melody. This is unresolved, right? This is the tonic. And we don't return to the tonic, so it's sort of an open thing. We don't resolve. It's very soft, but you can hear the strings with their oscillation below everything else. Sorry about that, that's the projector just timing out. We'll fast forward just to the end so that we can hear this sense of ambiguity as it's achieved. Is it on? Sorry about that. Well, we'll wait for it to turn on. But that was the last musical example I had, so while we wait for that, anyone have any unresolved questions that can bring up? That all made perfect sense? Yeah.
In terms of form, what do you think relative to kind of this modern sort of version of symphonic orchestra where it's very like not, it's purposefully not put together? You know what I'm talking about? That type of music, like, so where would that fit into form? It seems like it's a big popular thing right now, is to compose music that has no sort of general form or rhythm that ties together.
Right. So it actually does have form. It's just not immediately apparent. And the reason, the reason that it no longer has the classical forms that we adhered to in the 18th and 19th centuries is that we sort of, the ear has grown tired of those, so to speak. We've heard them enough times that they've become predictable. So now new areas of making form include, instead of having a melody dictate your piece, having a rhythm dictate your piece, like in Stravinsky's Rite of Spring. That entire movement is based off of that polyrhythm. There isn't really a strong melody, it's just sort of random notes played. The notes actually don't matter. If you try and plot the melody, it doesn't make any sense. It's the rhythm that's driving it. In more modern music, instead of rhythm, you might have some other process driving it, like recurrence of a certain interval. You could have a perfect fifth, and the actual notes of it don't matter, but that interval is repeated over and over and over again, and that creates the form. So it has some element of order, right? It could be predictability, it could be recurrence, symmetry, whatever. The order is just variables. It's not necessarily one of those things we discussed, it just has some element of order. Close it back on. Let's just listen to the last minute or so. Now we can definitely hear this string oscillation, and it's getting higher and higher. The tonic is about here, so it's correcting it. Does indeed end on the tonic, but it's very abrupt. It doesn't have that 5-to-1 or strong finality that we're used to in music. It creates this ambiguity at the end where we're left, with did it actually resolve or did it just end in that oscillation? Anyway, that's all I have. Feel free to ask more questions if you have, and here's a handout that you can take on your way out with some more recommended recordings.